Welcome back to the Masterclass. We've spent most of this course diving deep into the high-vacuum world of mass spectrometry. We've learned to love the sound of turbopumps and the silence of a 10 to the power of -7 torr manifold. But today, we're stepping out into the fresh air, literally. Have you ever felt like nanoparticles are like ghosts? They are all around us, in the smog of our cities, in the mRNA vaccine formulations. What if you could filter them in the very air we breathe? Most people think precision requires a vacuum. A specialist knows better. Today, we master the Differential Mobility Analyzer, or DMA. This is your atmospheric sieve. We are moving outside the vacuum to capture real-time precision in the ambient world. We are going to learn how to measure things that are too large for traditional MS, but too small for standard light scattering. This is where you find the truth about polymers, viruses, and engineered nanoparticles. Our briefing today covers 4 strategic chapters. Chapter A: Why DMA is the unique outlier. Chapter B: Mastering the concentric architecture and sheath flow. Chapter C: Selecting identity using voltage as your gatekeeper for size. And Chapter D: How to turn these physics into a 4-minute ROI for gold nanoparticles and viral characterization. The DMA has a distinguished pedigree. It started with Hewitt in 1957 and was refined by Knudsen and Whitby in the 70s. But the game changer happened in 1996 when we integrated it with electrospray, ES-DMA. Specialists' insight. The difference between an operator and a pro is knowing that you don't always need a vacuum pump to achieve sub-nanometer resolution. While others fight for space inside a manifold, the DMA breathes in a continuous flow of gas at atmospheric pressure. How does it work? Imagine a river. This is our sheath flow, Qs. It's a massive volume of clean laminar air, moving at a precise rate. Now, imagine a slit in the riverbank where we introduce our fish, the aerosolized ions. This is the aerosol flow, QA. The river wants to carry the fish straight down to the bottom. But we have a trick. We use a central collector rod as a giant magnet. Every ion feels 2 opposing forces, the electrical force pulling it toward the center and the drag force of the gas pushing it downstream. Where the ion lands on the rod depends entirely on its electrical mobility, ZP. High mobility ions, the fast swimmers, hit the top of the rod. Low mobility ions, the heavy drifters, land further down. We are sorting by aerodynamic behavior in real time. Voltage is your gatekeeper. You aren't scanning for mass. You are scanning for the perfect aerodynamic stride. We use Stokes's law to link mobility to size. By adjusting the voltage, we choose exactly which mobility diameter, dP, is allowed to exit through the sampling slit. We even use the Cunningham slip correction factor, because when particles get smaller than the mean free path, they start to slip between gas molecules. Enter the condensation particle counter, or CPC. Think of this as the magnifying glass. We mix the aerosol with butanol, or water vapor. The vapor condenses on our tiny particles, growing them into giant 10-micrometer droplets that we can count optically. If the concentrations are too high, we switch to an aerosol electrometer. A pro knows which detector to use based on the crowd density of the sample. This is where the ROI becomes real. Ever wonder if your nanoparticle synthesis produced the size you wanted? Don't wait 3 days for the TEM results. Use the DMA. In just 2 to 4 minutes, we can determine the diameter and the absolute number concentration. We can even see if the particles have aggregated, because they show up as distinct mobility peaks. It is the tactical choice for high-speed synthesis validation. Consultant's secret. We use DMA to fill the strategic gap. It's the perfect tool for characterization of self-assembled monolayers, SAM. When you coat a 10-nanometer gold particle with μA, the DMA sees that change instantly. We can calculate the coating thickness, delta L, by observing the shift. It's the difference between guessing and proving. Simple interpretation, broad size range, no vacuum required. Summary: the ambient advantage. We've learned that ES-DMA is the ultimate tool for characterizing broad size ranges. We've mastered the river and the magnet. Remember, don't bring the sample to the vacuum. Bring the measurement to the sample. Real-time truth happens in the air. You are now an ambient specialist, capable of characterizing the invisible ghosts of the aerosol world. You've mastered the physics of measuring shape and size. But in a global industry, you don't always need to reinvent the wheel. Join me in our next unit, Module 4 to 11, Knowledge is Power, where we learn to leverage global CCS databases to instantly confirm suspect identities. We are moving from measuring to matching. I'll see you in the database. Any final questions on ambient flow or nanoparticle sizing?